Hello, this is Mr. White, and in our previous video we went over the Rolle's theorem and the mean value theorem. This one will focus strictly on the mean value theorem, and I'm calling it part 2. So let's take a look at the two exercises we'll cover this time. Now, in a previous video we were instructed to use a graphing utility to perform certain tasks, and I said at that time, let's put the graphing calculator aside. We don't need it. We can do this by hand. I could still make the same claim here. We could do this completely by hand, to be clear, but I'm going to say let's just make the choice to go ahead and use the calculator and not strive just to get the answer, but to get there as efficiently as possible. So in this exercise we are instructed to use the graphing utility to graph the function f. That'll be simple enough. Find the secant line between the endpoints. And then finally, graph any tangent lines that are parallel to that secant line. And I trust you recognize the mean value theorem, how that's coming across in that problem statement. So let's go ahead and do part A. Bring the calculator on the screen, and I've already entered in that function. Now, if I were just to go to zoom standard, zoom number 6, I would see this. And that's not a bad view of the graph for certain other purposes, but it's not our best view for this exercise. Remember, I'm supposed to be interested only on the interval from -2 to 1. So if I were to change the x-min and the x-max from -2 to -2 and 1, I'm going to see it's still not a great view of the graph. I'm wasting a lot of space up at the top of the screen and at the bottom of the calculator screen. So what would have been a better choice for me to have done before changing those settings is to go ahead and trace to the one endpoint, -2, and see what kind of y values I'm dealing with. I'm dealing with the y value of -1 here, and I could just look visually and see that that looks like it's probably the lowest point on the graph on this interval. So I don't need a y min much lower than -1. Similarly, if I trace to the other endpoint, 1 there, I see that there I'm dealing with a y value of 2, so I don't need a y max much bigger than that. So what would have been a better choice is to trace to those 2 points early, first thing, and then go to something like -2 to 3 on my y min and y max. I'm just leaving a little bit of room above and below, but I see that by doing that I get a much better view of this graph here, or at least the region of it that we're interested in. And so that's going to be part A. You would sketch something like that on your assignment page. So let's call that part A. And let's also look ahead to B and C and get a sense of, again, what is it specifically we're looking for here? Well, for part B, where we're asked for the secant line, that's where we're going to find the equation for this line. And as far as part C goes, any tangent lines that are parallel to it, looking at the graph gives us a clear expectation that we're looking for 2 tangent lines. We're looking for one of them up here, and we're looking for another one down here. So our goal for parts B and C is to find the equation for those lines there. Let's start with that secant line. And again, that's the one in the middle here, right? So we had said earlier that this point had coordinates of -2, -1, and 1, 2. So for part B, finding the secant line, let's bring up the mean value theorem here and remind ourselves where that is present in the mean value theorem. So remember that that's the right-hand side of this formula. The f of b minus f of a over b minus a, that was the slope of the secant line. y2 minus y1 over x2 minus x1. So let's go ahead and do that. The secant slope is going to equal the f of b minus f of a. So that's going to be 2 minus -1 over b minus a. That's going to be 1 minus -2. And that's going to equal 3 over 3, which just equals 1. Now, to find the rest of the equation for the secant line, we'll use our trusty y minus y1 equals m times x minus x1, our point slope form. And remember, the slope that we just calculated here, that's our m value. Now, as far as which endpoint should I use for the x1 and the y1 values, I really have a choice. I could use either this one or this one, and it would really give us exactly the same result. And if you're not convinced of that, I certainly invite you to pause and try it out for yourself. Most students tend to want to use the one that doesn't have the negative sign, so let's go ahead and use that. X minus, that's our x1. And then y, on the left side, y minus y1, we'll use that y value. And as I've said multiple times before, for the purposes of homework and assignments, you may certainly put a box around that, but since we're going to be entering this into the calculator, we do need to rearrange it into slope-intercept form, and that's going to be, let's see if I distribute that and shuffle it around, that's going to be x plus 1, right? So let's go back to the calculator and enter that in, and we'll expect to see that secant line there. So I'll go to y2, and I'll do the x plus 1, and we'll just verify that we got that right, and it looks like we did. Okay, so next up, let's try to get those two tangent lines that are going to be parallel to that secant line. So I'll scroll down a little bit to where I have the MVT hiding out. And again, we just did the secant slope and all the rest of the secant line. And remember, we need it to be parallel to the tangent slope, because that's what it means for two lines to be parallel, is that their slopes will be equal. And remember, that's what the derivative is the slope of the tangent line. So our next step is to find the derivative of the function, the original function, and set it equal to that secant slope, which, remember, was 1. Okay, let's move this off to the side. And we can see there, I've got the original function visible here, so let's calculate its derivative. I'll put c, and fortunately for us, that's a pretty easy derivative to calculate. We're going to get 3x squared plus 4x, and then plus 0, which I won't bother to write. So according to the MVT, we're going to set that equal to the secant slope. So let's do that. So just to be explicitly clear, tangent slope is the 3x squared plus 4x, and we're setting it equal to secant slope, which was simply 1. And let's proceed to solve that. That looks like a quadratic that probably won't factor. We always are crossing our fingers that this would be able to factor, but this one will not. So we either do completing the square or quadratic formula. I'm going to say let's go ahead and do quadratic formula. Okay, there, I did it for you just to save a little time. And I bring the calculator onto the screen, and there's my -2 plus root 7 over 3. There's my decimal approximation. I do second, and I'm hitting the enter button right now. So second enter, and let's do second left, and then back over to the right a few times just to replace that plus with the minus. And there are my two values. Let's double check and see if they both are on the interval that we're interested in. Our interval was from -2 to 1. They are both on the interval, and we expected that because we expected to find two tangent lines, right, that are parallel to the secant line. So again, if we're doing this all by hand, I would obviously work with this expression of x, or the c values, so to speak, for the mean value theorem. Remember, we're calling them x, but those are really this c value that we're looking for. But since I said let's go ahead, we're instructed to use the graphing calculator, and I said let's go ahead and use it. Let's do this intelligently here. What I'm going to do is I'm going to arrow back up to that value, and I'm going to enter it, or I'm going to stow it as alpha a. Actually, let me store that one as b. just because it's the bigger of those two values, and I just tend to like to make the smallest value A and the bigger one B. Now let me go back to this one, hit enter, and then I'll stow that one as A. So I've got my two points where the tangent line is going to be parallel to the secant line. I've got those x values stowed as A and B. And again, since we're allowed to use the calculator, let's do so intelligently. Let's go back to the graph, and I'll go to secant, draw, and I'll go to number 5, tangent. So I just click the number 5, and I'll say, where do I want the tangent line? I want it at alpha A. Enter. And look at that. And graphically, we see that, yes, it certainly does look parallel to that secant line. Let me drag that on here. And let's do the same thing for B. Secant, draw, number 5, tangent. Let's do alpha B. Enter. And again, I get a visual confirmation that, yes, that does look like the line that we wanted. So here are two tangent line equations. And we would just write that on our paper. Now we know to ignore all those extra digits in the equation. We know that this will just be 1x. That's our calculator being goofy. So that's y equals 1x, or just x, plus this number, 1.631. 1.631. And then this one over here, similarly, we'll do y equals x, and then minus 1.112, that number right there. And that was part C of our exercise. Okay, let's go on to the next exercise. Here we have a ball thrown upward from a 150-foot tall building with an initial velocity of 50 feet per second. We're going to find the average velocity during the first 4 seconds. And we're also going to use the MVT to verify that at some point during that 4 seconds, the rate at which it is falling instantaneously is going to be the same as that average velocity that we got in part A. And we're going to find out at what time that occurred. So let me move part B off to the side, just clear up a little space. And we're going to find the average velocity. And I find it helpful to, again, draw a little picture that represents this situation. We've got a building. It's 150 foot tall. And a ball is going to be thrown upward, and then it come back down. And again, we're really envisioning that this horizontal axis represents time. And one thing that I forgot to mention a moment ago is that at this point in the course, you will be provided the free fall position equation. Later on, when we get into integration, you'll be expected to come up with that on your own. But for now, you'll be given the free fall position equation. And there it is for you. Let's plug in the relevant numbers. If you recall from earlier work, this would be negative 16t squared, and the v subscript 0 is the initial velocity, the velocity at time 0, which we said is positive 50. Positive because it's being thrown upward. If it were being thrown downward from the building, then we'd use negative 50, right? But this is positive 50 t plus the initial height, the height of the building where this ball started out when the stopwatch read 0. So plus 150. Okay? The fact that this problem, this exercise states to find the average velocity during the first 4 seconds seems to imply that it's going to take more than 4 seconds to do this total trip. So let's assume for the moment, and we'll find out if we're wrong, but let's assume that 4 seconds, let's say that this right here is at 4 seconds, and that the ball has not reached the ground yet in that 4 seconds. And if we're trying to find the average velocity of the object, think of what velocity is. Or at least average velocity. Average velocity is defined to be the change in position, so delta s over the change in time, delta t. Or in this particular case, since we're talking about over the first 4 seconds, s of 4 minus s of 0 over 4 minus 0. And again, you're starting to see the mean value theorem come out here. Visually, over here on our diagram, here's the initial point, and again, here was our 4-second point, and we recognize that this calculation here is just the slope of the secant line that connects them. So average velocity, this is a major point. When you think average velocity, recognize that on a position versus time graph, average velocity is the secant slope here. Okay, so let's go ahead and calculate that. Let's do some mental math here. We're trying to calculate S of 4. So if we plugged in 4, 4, 4, we would get negative 256. That's negative 16 times 4 squared. Plus 200, that would be negative 56. And then plus 150, that would bring us up to, let's see, 94. All right, and then if I calculate S of 0, that's a little bit easier. 0, 0, 0. We're clearly going to get 150 there, right? So minus 150 over 4. That will be negative 56 over 4, which is negative 14. And let's go ahead and put the units in there. Feet per second. That is our average velocity. And again, that is the slope of this line here, the secant line. Not too bad, right? Okay, for part B, we are to use the MVT to verify that at some point during the first 4 seconds of the fall, the instantaneous velocity equals the average velocity. And again, here's where I really feel that drawing a little sketch off to the side, even if you weren't asked to, just drawing that sketch helps you make these connections, that we see the MVT here. We envision a tangent line being parallel to the secant line. We can tell that, yes, there is a value, some value C, that is between 4 and 0, and we're going to find it. And we know that we start by finding the slope of tangent lines as given by the derivative. So let's go for the slope there. S prime of t. And of course, I'm looking up top here at our S of t, which is still barely visible on the screen. And if I take the derivative, I get negative 32t plus 50. And given the sort of physics context here, I of course have to point out that, do you remember what S prime of t is equal to? It's equal to instantaneous velocity, and that's denoted by v as a function of time. So not v average, but instantaneous velocity at any time t can be given by this equation. So what are we going to do here? We're going to set this instantaneous velocity equal to the average velocity. And once again, just to be absolutely sure, I bring the mean value theorem back on the screen, and let's make absolutely sure you see the connection that just because we're using different letters, this was f of b minus f of a, whereas we are using s of 4 minus s of 0, etc. But let's make sure that you see that's the same thing. This over here was our instantaneous velocity, s of t, or s prime of t, right? All right, so the MVT says we shall set those quantities equal to each other. So let's set the instantaneous velocity, negative 32t plus 50, equal to that average velocity of negative 14. Let's subtract the 50. That's going to be negative 64. And very conveniently, it works out that t equals 2, which in this case is in seconds, so I'll put 2 seconds. So back on our picture up here, we have found that the point here at which the tangent slope is equal to the secant slope, turns out that is at 2 seconds. And I'll ask you to ponder this. I'm not going to answer this right here, but do you think it's coincidence that that 2 just happened to be halfway in between the endpoints of the interval? Does it always work out that way? I'll let you ponder that as you do homework exercises. But I think we're done here. We used the MVT. We verified that, yes, there's a value at which those slopes are equal, and we found that time. There it is.